This is the reaction between weak acid and strong base. It is actually almost the same as the strong acid weak base titration. So if you look at to this titration curve, there are several distinct regions that we have to know in this reaction between weak acid and strong base. When the first point is the initial pH is quite high. Okay, the initial pH is quite high because this is a reaction between weak acid. So the concentration of the H3O plus is not as high as the concentration of the H3O plus in a strong acid. And then the second point is when we observe that the gradual increase of the pH. Okay, and this region is what we call as a buffer region, because at this region we start to have a mixture of a weak acid and its salt. And then the third point is the equivalent point. Okay, we have a steep increase here, and this is the equivalent point, and the value is greater than 7. And this is the fourth region when we observe that the gradual increase in the pH until it is constant at the end of a process. So let's calculate the pH of the solution during the titration between a weak acid and strong base. We have a propanoic acid that is reacted with the sodium hydroxide. So we have to identify what is the titrant and what is the titer. So let's imagine the process. We have a pipette. Okay, and then we have a conical flask. And we have a solution and also the pH meter. What we have in this conical flask is actually propanoic acid, HPR, with the volume 40 ml and also 0.1 molar, while what we have in this burette is sodium hydroxide, 0.1 molar. How do we know that the one in this conical flask is the HPR? Because the actual amount and also concentration is given. Fixed amount, which is 40 ml, fixed volume, which is 40 ml, and also the concentration. However, for the sodium hydroxide, okay, no volume is given. And then the question also said that after adding the following volume of the sodium hydroxide, shows that sodium hydroxide is the one in the burette. Okay, so let's look at 2a. We have to calculate the pH before the addition of any sodium hydroxide, means that the pH that was contributed by the HPR only. So we know that HPR is a weak acid. For A, we have HPR, add with the H2O, reversible arrow turns to PR minus plus H3O plus. So initial concentration, HPR is 0.1 molar, H2O dash 0 and 0. Concentration change minus X plus X plus X. So the concentration at the equilibrium, 0.1 minus X, X and X. So we can calculate the pH if we know what is the concentration of the H3O plus. So we have to solve X. So to solve X, we assume that the X can be neglected because of a small Ka value. Ka is equal to concentration of the PR minus multiply concentration of the H3O plus over concentration of the HPR, which is equal to, given Ka is 1.3 times 10 negative 5 is equal to x squared over 0.1 minus x. So since that we have a small Ka value, so this x can be neglected. So to solve x and get the concentration of H3O plus equal to x is equal to square root 1.3 times 10 negative 5 multiply with 0.1, so it is equal to 1.14 times 10 negative 3. Okay, so we have the concentration of the H3O plus, so we can calculate the pH is equal to negative log H3O plus concentration, so it is equal to negative log 1.14 times 10 negative 3, and it is equal to 2.94. Let's look at 2b. This is after the addition of 30 ml of the sodium hydroxide. So to start the calculation, we have to calculate the mole for each one. N for HPR is equal to 40 multiply 0.1 over 1000 is equal to 4 times 10 negative 3, and then N for the sodium hydroxide that is added is equal to 30 ml multiply with 0.1 over 1000, so it is 3 times 10 negative 3. And then the V total after the addition will be 40 plus 30, so 70 ml equal to 0.07 liter. So it is important to calculate the V total because later we have to calculate the new concentration. Okay, let's construct the reaction table. We have a reaction between HPR and sodium hydroxide. It turns to NaPr plus H2O. So N initial HPR is 4 times 10 negative 3, sodium hydroxide added is 3 times 10 negative 3, and APR 0, H2O dash. And change, let's compare between these two, HPR and sodium hydroxide, their ratio is 1 to 1, but when we look at to their amount, we know that sodium hydroxide is the limiting reactant because it is less than HPR, so it will be completely consumed. So negative 3 times 10 negative 3, here negative 3 times 10 negative 3, plus 3 times 10 negative 3, so and final will be equal to 1 times 10 negative 3 mole of the HPR that is left, no more sodium hydroxide left, and we have NaPr that is formed is 3 times 10 negative 3 mole. And then when we look at to what we have, the components that we have in the reaction vessel after the addition of 30 ml of the sodium hydroxide is we have HPR and we have NaPr left, no more NaOH. So we know that HPR is a weak acid and then NaPr is the salt. So we are actually have the mixture of the weak acid and salts, or at the same time we know that we have a buffer system. So when we have a buffer, we know that we can calculate the pH of the buffer system by using Henderson equation, and we know that the system is acidic buffer system, so we can strictly use the equation of the pH equal to pKa plus log concentration of the salt over concentration of the acid. So it is equal to negative log 1.3 times 10 negative 5 plus with log salt is 3 times 10 negative 3 over the new volume 0.07 liter over the concentration of the acid is 1 times 10 negative 3 over 0.07. So we get the pH is equal to 5.36. Okay, let's look at to C. It is after 40 ml of the sodium hydroxide is added. So as usual, firstly we have to calculate, or we have to know what is the initial amount of the HPR, which is 4 times 10 power of negative 3, and then the amount of the sodium hydroxide is added is 40 ml times 0.1 molar over 1000, so it is 4 times 10 negative 3 as well. When we look at to their same amount, we know that this is a point at the equivalent. Then we can calculate the V total is equal to 40 plus 40 is equal to 0.08 liter. Okay, 40 ml for both. Okay, let's construct the reaction table of a reaction between these two. HPR plus sodium hydroxide turns to NaPr plus H2O. So N initial for HPR is 4 times 10 negative 3, NaOH 4 times 10 negative 3, NaPr 0, H2O dash. So N change both negative 4 times 10 negative 3, negative 4 times 10 negative 3, and APR form positive 4 times 10 negative 3 dash for H2O. So final will be 0 for HPR, 0 for sodium hydroxide, and we only have an APR left, 4 times 10 power of negative 3. So the pH that is measured in this conical flask after the addition of the 40 ml of the sodium hydroxide is only contributed by the NaPr. So let's refresh back how to calculate the pH of a salt solution. Okay, so we have NaPr. A salt will dissociate into its ion Na plus and Pr minus. So we know that Na plus comes from strong base, so that it will be weak conjugate acid, while Pr minus comes from weak acid, so Pr minus will be strong conjugate base. So Pr minus is the one that will further hydrolyzed. So let's construct the hydrolysis table for the Pr minus. So we have a Pr minus react with the H2O, reversible arrow turns to HPR plus OH minus. In this ice table we are using concentration, so we can calculate the concentration final here. 4 times 10 negative 3 divide with the total volume 0.08 liter. So the concentration of the NaPr is equal to 0.05 molar. So we have 0.05 molar of the NaPr, 0.05 molar of the Na plus, 0.05 molar of the Pr minus. So that the initial concentration of the PR minus is 0.05 dash H2O, 0 HBr, 0 hydroxide, concentration change minus X plus X plus X, concentration at the equilibrium will be 0.05 minus X, X and X. So we know that PR minus is a base since that hydroxide is liberated. Okay, and what's given to us is the Ka value. We know that we have to solve the X to get the concentration of the hydroxide ion. Ka is given. So the first step is to calculate the Kb for the PR minus. So Kb is equal to Kw over Ka, 1 times 10 negative 14 over the Ka that is given is 1.3 times 10 negative 5. So that the Kb is 7.69 times 10 negative 10. Okay, let's continue. Kb just now is 7.69 times 10 negative 10. So we can calculate the X value, which is equal to the concentration of the hydroxide ion, is equal to square root Kb 7.69 times 10 negative 10 multiply with the initial concentration of the PR minus just now is 0.05. Okay, how do we get this equation? Is when the X is neglected. So we will get the concentration of the hydroxide ion is equal to 6.2 times 10 power of negative 6. So we can calculate the pH is equal to 14 minus pOH. It is equal to 14 minus negative log concentration that we get here. So 6.2 times 10 power of negative 6, and lastly we get the pH is equal to 8.79. As for D, it is when 50 ml of the sodium hydroxide is added. Amount of the HBr is 4 times 10 power of negative 3 mole. And then we calculate the number of mole of sodium hydroxide that is added is 50 times 0.1 over 1000. It is equal to 5 times 10 negative 3. So V total is equal to 40 plus 50 ml. So it is equal to 0.09 liter. Okay, construct the reaction table. So it is a reaction between HBr plus NaOH turns to NaPr plus H2O. So N initial HBr is 4 times 10 negative 3. Sodium hydroxide added is 5 times 10 negative 3. NaPr 0, H2O dash, and change is negative 4 times 10 negative 3, negative 4 times 10 negative 3, positive 4 times 10 negative 3. This is because HBr and sodium hydroxide's ratio is 1 to 1 and HBr is less than sodium hydroxide. So HBr is limiting reactant and completely consumed. Therefore, N final will be 0 for HBr, sodium hydroxide 1 times 10 negative 3 left, and NaPr form is 4 times 10 negative 3. So let's look at to the components in our conical flask. After 50 ml of the sodium hydroxide is added, we have strong base and salt. Okay, so if we compare between the pH of the salts and sodium hydroxide, we know that the pH in this container majorly contributed by the strong base. Therefore, we will calculate the pH 1 times 10 power of negative 3 mole of sodium hydroxide that is left. Okay, before that we calculate the concentration final, or it is 1 times 10 negative 3 divide with the new volume 0.09 liter is equal to 0.011 molar. So pH is equal to 14 minus pOH. It is equal to 14 negative log concentration of hydroxide, which is 0.011 molar. Then we'll get the pH is equal to 12.05. So we can complete the answer here. After 50 ml is added, the pH of the solution is 12.05. From this pH that we have measured, okay, we can construct the titration curve of the reaction of this weak acid strong base. So it is like this. Okay, it starts here and then gradually increase, and this is the buffer region, and then we have a equivalent point above 7, and then gradually increase and constant. So if we have a reaction between this weak acid strong base, okay, we'll use the phenolphthalein as the indicator. You have to memorize this. Phenolphthalein is used for this weak acid strong base titration. Okay, and then this is a weak base strong acid titration. Okay, if you look at to the starting pH, it is around 11. We know that the one in the conical flask is a base. Okay, because the starting pH is basic above 7, and then the acid of HCl is in a burette. So let's look at to the titration curve. This is the initial pH, and then the pH decreases. Okay, and this region we call it as the buffer region, because in this region it consists of the ammonia and its salt, ammonium chloride. Then we have a steep here, and this is the pH at the equivalent, which is less than 7, and then decrease more, and it is constant. So if we have a reaction between this weak base strong acid, we'll use a methyl red as the indicator. The method to calculate the pH at 4 different points are the same as what we have discussed in strong base weak acid titration. So these are the list of the acid base indicators that we have. Okay, you can look at to the range, okay, of each one. If you look at to the phenolphthalein, the range is between 8 to 10. The methyl red is for the acidic salt. Okay, the range is 4 to 6. Okay, this is the changes of the color of the bromothymol blue. Okay, according to the pH. If it is less than 6, it is yellow, and then this is to 7.6, and this is greater than 7.6, blue color. So see you. Assalamualaikum.